All right, guys, this is your explanation for chapter 17 on reaction rates. So finding the change in the quantity and dividing it by the change in time determines a rate. So there's different types of rates, like for example, the speed that you drive on the freeway or on the roads. Those are rates. It's the change in quantity over the change in time. So to remind you, this triangle is the Greek letter delta, and it means the change in. So this is the change in quantity, whatever you're talking about, divided by the change in time. So like, for example, again, if you're driving on the freeway miles per hour, that is the change in quantity would be the amount of miles, and the change in time would be the 1 hour. We're talking about concentrations of substances in a chemical reaction. So that's what we're talking about when we're talking about a reaction rate. Is like how fast a substance forms, or how fast a substance decomposes. And so we are going to denote the concentration of a substance by putting it in brackets. So for example, here, this is NO, this is nitrogen monoxide. And the fact that it's in square brackets, that means that you would read that as the concentration of NO. In other words, how much NO, okay? That's what we mean when we say concentration. So a reaction rate for a chemical reaction is the change in concentration of a substance per unit time. All right, for this unit, you need to understand something called the collision theory. The collision theory states that atoms, ions, and molecules must collide in order to react, but they must also collide in the correct orientation and with sufficient energy. So basically, you guys know collision means that two things come and, basically bump into each other. They collide. So that has to happen. If there's no collision, then there's not going to be a reaction. So first of all, they have to collide. But it's not enough for them to just collide. They have to also collide in the correct orientation. And then what that means is that they have to line up correctly. Like when you're putting a puzzle together. If the puzzle piece looks like it belongs there, but it doesn't match, it doesn't line up correctly, then it doesn't belong there. So they need to line up correctly. And that's still not enough. They also have to have sufficient energy. In other words, there has to be enough energy for them to form a reaction. So all three things must be met. They have to collide in the correct orientation and with sufficient energy. Those are the 3 points of the collision theory. So during a chemical reaction, there's lots and lots of collisions, but not all of them are going to produce a reaction because some of them are not lined up correctly or they don't collide with enough energy. So even if they bump into each other, there's still not going to be a reaction if they don't have the correct orientation or if they don't have enough energy when they collide. But if they do meet all 3 criteria, if they do collide with correct orientation and enough energy, then what forms is what's called the activated complex. All of these atoms stick together. It's a temporary and very unstable arrangement of atoms, and then they immediately break apart into the product. So they just momentarily stick together. And so it's a short-lived complex, and it's formed during what's called the transition state. And on the graphs, we'll point out to the transition state. To get to that point, to get to the transition state, they have to have sufficient energy, like we said before. That sufficient energy is called the activation energy. So the energy that's required for reactants to overcome in order to form the products is called activation energy. So on a graph, you'll be able to see if it takes a lot of energy for a reaction to happen or not, depending on the height of the activation energy hill. So here's the 2 graphs. This graph shows an endothermic reaction. This graph shows an exothermic reaction. So see, this is where the starting point is. This is where the reactants start. On both graphs, the starting point is where the energy of the reactants is. So then the reactants have to have sufficient energy to get to the top. And that's called the activation energy here. Okay, the sufficient energy to get to the top. And then from there, that's where the transition state is. So the top of the hill is the transition state. That's where the activated complex lives. And then it will immediately break apart into the products. Same thing with the exothermic reaction. It's the same exact thing. Here's where the reactants start. They have to have sufficient energy to get to the top of the hill. At that point, all the atoms are stuck together in the transition state. But then they'll immediately break apart and form the products. So the difference between these two graphs is that this one, you see how the products are at a higher energy than where the reactant started? That means energy was absorbed. Therefore, it's an endothermic reaction. Whereas in this graph, the products end up at a lower energy than where the reactants began. So therefore, this reaction released energy, and that's why it's an exothermic reaction. So in the next section, there's factors that will affect reaction rates. So there are 5 factors that we're going to talk about. The first one is the nature of reactants. In other words, simply by nature, some substances are going to be more reactive than others. So you guys recall from when we learned about valence electrons at the beginning of the year, sodium is in group 1, and it only has 1 valence electron that's going to get rid of, whereas calcium is in group 2. And it has 2 valence electrons that it needs to get rid of. The fact that sodium has only 1 valence electron to get rid of, it's going to make it much easier for sodium to react. So Na is simply much more reactive than calcium because of its position on the periodic table, the fact that it has 1 valence electron. Number 2 is the concentration. So basically, if you have more reactants in a reaction, they're going to be able to collide more. And so if they're able to collide more, then there's going to be a more likely for a reaction to happen. The third factor is surface area. So surface area is when if you have a large piece of sugar, for example, if you've ever made Kool-Aid and you're dissolving sugar into the pitcher, you'll notice that it takes a long time for it to dissolve because it's a big chunk. It has a large surface area. But if you were to take that big chunk of sugar and break it apart into smaller pieces, then you're going to increase the surface area by spreading it out more, and therefore there's going to be more surface area for the particles to collide. Again, more collisions, more reactions. So again, we're focusing on those collisions and on the collision theory. The fourth factor is temperature. So generally, we know that increasing the temperature is going to increase the movement of particles. So if you increase a temperature, the particles start moving faster and they get more kinetic energy. As a result, there's more movement, more collisions. Okay, so those are the first 4. The last one is either a catalyst or an inhibitor. A catalyst is something that will speed up a reaction rate, but it's not going to affect anything in the reaction. So for example, let's say you're looking at a living organism. If you heat it up, if you increase the temperature, it's most likely going to burn it and kill it, and therefore you're not going to be able to look at the reaction rate. But if you add something like a catalyst, then you don't have to increase the temperature. The catalyst will increase the rate of the reaction, but it won't cause any harm to any of the substances, and it also won't be used up in the reaction. So a really important visual that I want you guys to know is this graph here. So with no catalyst, you're looking at the blue line. The blue line has a much higher activation energy. In other words, you have to go from here all the way to the top of the blue curve in order to get to the transition state, right? That is a very high value for the activation energy. But what the red line illustrates is that if you were to add a catalyst to this reaction, the catalyst can give it a different route to get to the other side. It's like a shortcut. So now it only has to get to this point. It uses a lot less energy to be able to get to the other side. They both end up at the same final destination, but this one requires a lot less energy. So that's when you add a catalyst. So catalysts give it a different route for it to have a faster reaction rate. And the opposite of a catalyst would be an inhibitor. An inhibitor is a substance that slows down reaction rates. So here's some examples: weed killers, food preservatives, things like that. Those are inhibitors because they slow down reaction rates.